a derivative of 2x plus 3, I could have h of x, and I could have x squared plus 3x minus pi, and that again, all of those would have the same derivative. That's what this theorem is saying. Okay, nothing much except that. Now, again, I'm not going to give you time to write every word down because it will be coming. Name the steps in the process. We've already done that. Okay, in the process, to determine the derivative, we multiply the exponent to the coefficient, and the second thing we do then is to subtract 1 from the exponent. Okay, what are we going to do for the antiderivative? For the indefinite integral, this becomes 1, but we're going to add 1 instead of subtract 1. This would be our second step. We would divide instead of multiply. Okay. Rules for integration. Let's take a look at these. Trust me, you've seen these before. Not with integration, but you've seen them with other stuff. So let's see. Power rule. This is saying the same thing we just talked about. So for those of you who've never seen this before, and I asked the others, have you using a rule you memorized? This is the rule you memorized. You add 1 to the exponent and divide by the new exponent. Okay, that's the rule. Now, sum and difference. I say that you've seen this before. If you have the indefinite integral of the sum or difference of two functions, it is the sum or difference of the two indefinite integrals. Okay, so we've seen that one before. This is the coefficient, the indefinite integral of a scalar times a function is the same thing as the scalar times the indefinite integral. So again, those we've seen before. We're not going to really break them out and do too much different with them. Okay, so now let's jump to our first real example here. Determine, and again, I don't think this is 24, so we won't use that. Determine the indefinite integral. Again, that's what that sign represents. Now, there's all kinds of other rules we're going to come up with that are going to help us do things like composite functions and quotients and products and all that stuff. But for now, we're going to keep this pretty simple, just like we did with the derivatives. So instead of seeing this as a quotient, let's instead write this as x squared. I'll put a couple steps in here. X squared divided by x to the fourth plus 2x divided by x to the fourth minus 3 divided by x to the fourth. Those don't look like exponents, but they are. Dx, which would give us the indefinite integral of x to the negative 2 plus 2x to the negative 3 minus 3x to the negative 4 dx. Use the rule. Come up with the antiderivative, the indefinite integral of that. I'll give you a moment to work on it. This quantity in here has a name, and it's called the, it's the derivative. I'll put that in here. But because we're looking at an integral, we call it the integrand as well. So let's see, what did you come up with? Now, how will I know that you've done this correctly and you haven't just, punched in some numbers? Well, I've got some work I want you to show me, okay? Just like we have on derivatives. And here's the work. I want you to show me that you're adding 1. So if you didn't do this, go back and add this to your work now. Add 1 to the exponent, and then show me that you're dividing by that new exponent. Add 1 to the exponent, show me that you're dividing by the new exponent. Add 1 to the exponent, show me that you're dividing by the new exponent, and then plus c. Is it incorrect if you forget the plus c? Yeah, because we're talking about what functions will yield that derivative, and there's infinitely many. So our answer then would be, let's see, x to the negative 1 divided by negative 1 plus 2x to the negative 2 divided by negative 2 minus 3x to the negative 3 divided by negative 3 plus c, or negative 1 divided by x minus 1 divided by x squared plus 1 divided by x cubed plus c. How'd you do? Pretty easy stuff, right? It's just you have to think in reverse of what we've been doing in order to come up with that. Okay. We'll get as many done as we can. Oh, and I do, Chelsea, I do want to go back to that one problem. We'll talk about that just for a little bit, so if you can, help me, remind me about 7 minutes. We have time to do that. Okay, here's the next problem. Again, I don't know that it's problem 44 in the new text. Now, we've already looked at 4 divided by x, but chances are you're going to forget that as you're doing problems, and you're going to go through and put it down as 4x to the negative 1. And we're going to try to divide by the new exponent. And you know what's going to happen at this case. It's 0. Okay? So you can't divide by 0, so you're going to have to ditch that plan, okay, and come up with a new one. Now again, we just looked at this 4 divided by x, so hopefully you will remember that this is the same as 4 times the natural log of x. But here again, we need to decide what is the function that yields secant squared x. Now, if you don't remember, you might try using your Inspire. I don't know what, the Inspire seems to go to everything to sine and cosine. Have you noticed that when you use a trig function? Okay. In the front of your textbook, there's all kinds of special ones like this, so you can always do that. You can always look up on a derivative page and come up with that answer that's on a derivative page. So which one? Anyone know what function yields secant squared? Tangent. Are we done? Plus c. Okay? And again, you can try this by taking the derivative of this, or you can use the Inspire like we did over here and put it into your Inspire and see if you get the same answer. Okay. Now let's see, what else do we have here? Okay, sketch the graphs of 1/2 e to the x. Let's just do this. Let's see. I would like, how many of these can we do? I'm going to have, let's take the first 3 of you in the first table here. I want you to graph the function that has c is equal to 1. Table behind them, you can do c is equal to 2. Brandon and James, you can do c is equal to 3. Over on this side, let's have the first 2 tables do c is equal to -1. And starting with Hannah, Emma, and Chelsea, let's do c is equal to -4. Okay, so just graph that function. Okay, so how do the graphs compare? Let's take a look at these. Okay. Do they all have about the same shape to them? Yeah, they all have about the same shape. Okay, the next thing, what I would like to do, I would like you to place a tangent at x is equal to, well, let's take a look. What would be easy to do? X is equal to 1. And determine the slope of that tangent. Is that a 1.36 that I see on this one here? Let's see. Looks like someone's following your lead. 1.4. This person right here, whoever this is, would you please hover and press the plus key? Let's open those digits up to be more than just 1. What do we see? Whoops. Got a problem with this one. Let's see. We have e squared. Yeah, whoever this is, you typed e squared. Maybe you're in the process of changing that. It should be just e to the x. There you go. Thank you. What are you seeing on the screen? Those that have it. Slope is what? Same thing, which tells us that for all of these functions, regardless of the constant term, we're getting the same derivative. So what would the indefinite integral be that corresponds to this problem? Indefinite integral of what? Now to answer that, what are you going to put inside here? Think again. The derivative, okay? So we want the derivative. Now, again, this is where it gets a little confusing. Notice I used a small case f up here. I didn't use capital F. Yeah. You have to kind of let that kind of go in and out of your brain, okay? The cap f is only there when we're talking about both together. Otherwise, if I give you f of x and I say, find the derivative of this, you're still going to let this be the function. So this is the case. This is the function. What's the derivative? And the derivative would be 1/2 e to the x. Okay. We're not